Hello and welcome to Ethproofs Call number 2. This is an extremely special call for various reasons. It's a little bit of a celebratory call because of the recent events. It's also a record call in terms of number of participants. We have 140 people live now, and folks are trickling in. We actually maxed out the number of invitees on the Google Calendar invite. And Zoom only has support for, at least the subscription that we have only has support for 300 people. So let's see how that goes. We have 25 speakers today, and it's going to be absolutely packed with alpha and announcements and some fun stuff. So let me briefly share a few slides, and then we can get started with presentations. Okay, so if you're interested in continuing the discussion, there is a Telegram group which is public, Ethproofs_community. And yeah, today's call, as I mentioned, is going to be dedicated to real-time proving. In addition, the website ethproofs.org is fully open source and has been from day one. And if you'd like to contribute, please submit issues if you find bugs, or even better, submit pull requests. So this is the call schedule for 2025. We are on call number 2, where the first call was dedicated to zkVMs. We had about 25 zkVMs introduce themselves. And yeah, this call is on real-time proving. The next 4 calls are going to be very exciting, in my opinion. Call 3 is going to basically try and explain how we could potentially get to 1 gigagas per second on DL1 using zkVMs. Calls 4 and 5 are paired together. They're basically trying to answer what ISA should we enshrine, if any, within DL1. We're going to have proponents of RISC-V go first, and then suggestors of alternatives of RISC-V come after that. And then call 6, very, very important, security and formal verification. Now, today's agenda is so packed that we're going to do something a little unusual, which is to have a 2-minute break in between. So in the first part of the call, we're going to be talking about what's it be a couple of zkVMs that are now open sourced. There's some newly tracked zkVMs that didn't have an opportunity to introduce themselves in the previous call that can do so today. We're going to have a bunch of updates on things that we've been working on within the EF, so 5 short presentations. And then, in some sense, the main part of today's call is the talks on real-time proving. Some of these teams have already achieved real-time proving, and some of these teams are very, very close and will give us progress updates on where they're at. We're going to have this 2-minute break with an interesting surprise. And then we're going to have various speakers talk about different types of proving with GPUs, proving with ASICs, as well as distributed proving. Now, one thing I wanted to plug real quick is the House of ZK Ethproof Summit event, which is happening in Berlin very soon, June 10th. This is a totally organic event. The Ethproofs team is actually not directly involved. It was proactively led and organized by the House of ZK team, but I think it's going to be a fantastic event. And I think there's limited seats, and we're close to the limit already. So do make sure to apply if you'd like to join in Berlin. Now, one of the things that I'd like to do here is just highlight probably my favorite piece of hardware now that I've discovered it, which is the Raspberry Pi Pico 2W. And the reason why I highlight it is because I believe that this device can actually run a fully validating Ethereum node, both the consensus layer node and the execution layer node. And of course, the way that we would achieve that is through ZK, and you can have validators and wallets and all sorts of entities basically just run on this type of hardware. It costs $7. It has Wi-Fi connectivity, so you just plug it to the wall. You don't need a host computer. And amazingly, I discovered this morning that the CPU is actually a dual-core RISC-V. So if we do end up having RISC-V zkVMs, there's a little bit of an inception here where we're using a RISC-V CPU to verify execution of RISC-V, which is kind of cool. And it's ultra low power. It's less than 1 watt, which is less than $1 per year of electricity consumption. So if you are kind of this decentralization maxi cypherpunk, I think this is the new benchmark. No normal Raspberry Pi. We're now aiming for the Raspberry Pi Pico. Now, this is the updated tracker of zkVMs. And since last time, I wanted to highlight a few things. One of them is that we now have more open source zkVMs. So we have Petra, which is open source. We have X, that was open source today. And we have Boojum 2.0, which will be open sourced imminently. I guess I wanted to, so Petra has already been announced, and I wanted to open up the floor to John to say a few words about the open sourcing that happened today. John.
Hi, everyone. So this is the X zkVM. We just open sourced it this morning after a lot of fun back and forth with Justin and folks. It is, this is like a pre-alpha state, so a lot of things are still broken, but the skeleton of the repository is there, and we released this to illustrate sort of this idea of using Lean 4 to act as the source language for zero-knowledge proofs. And specifically this idea that we're calling zero-knowledge proof carrying code of compressing the formal proofs into a zero-knowledge proof. And we have a whole bunch of examples of what this can be used for. And the example that I want to just take a few seconds to talk about is this idea of embedding Fermat's last theorem in from the margin of Fermat's margin note. And so you can actually fit a Gross16 proof in the same amount of space that margin note is. And so this mechanism with the Lean 4 formalization can take the entire Lean 4 formalization of Fermat's last theorem and turn it into a zero-knowledge proof. Can't do it yet. The formalization is not done. We're not. That's being done at Imperial College London. But the goal of this project is eventually to do this and fit the whole proof into the margin. And this is really useful because ultimately, when everyone on a lot of people on this call are doing formal verification things, what we want to do is be able to offer you guys the possibility of taking your formalization work and compressing it into a proof so you can ship it to your users really, really easily.
Okay, amazing.
Okay.
Thank you so much, John. And yeah, congrats on open sourcing, and very exciting because X is a very, very unique ZK VM. Now, unfortunately, Boojum 2.0, even though they were hoping to open source by today, they had a little bit of a delay. So I don't want to leak too much alpha, but I'm hoping that within the next few days, by the end of this month, there will be open sourcing happening. Now, the other thing that I wanted to highlight is that there are more zkVMs that are being tracked. One of which is still redacted. I guess one clue that I'll drop is that it is a Fortune 500 that is looking to build a RISC-V ZK VM, which is quite exciting. And so what I'd like to do is basically go through these new ZK VMs and give them an opportunity to introduce themselves in a couple minutes, starting with Ligero, and I believe Mutu will be presenting.
Hi, everyone. Let me just quickly share my screen. Thanks, Justin. Great intro. Really incredible to be part of this group of people who are pushing the boundaries of zero knowledge, having been studying zero knowledge for about 2 decades. I'm putting up this thing that Justin already talked about, his fascination for the Raspberry Pi Pico, and this is a question we want to entertain at Ligero. So let's no, that's okay. Sorry. What's Ligatron Zero Knowledge? It's the Ligero-based zero knowledge proof that we are developing at Ligero Inc. It's memory efficient, and there's a technical term what I mean by memory efficient, and it's a zkVM based on the WebAssembly intermediate representation. Today, this zero knowledge proof on a Chrome browser on Apple M4 Max, we can prove about 27,000 Poseidon hashes and 1,000 EDDSA on the BN254 prime, not a small prime, but the 254-bit prime per second. And I want to say that you give a faster GPU. I think on the 5090, this is like more than maybe 3.5 to 4 times faster on a single 5090. So really, here is a question that I think is possible, one that we might be able to demonstrate sooner, is that, you know, if you consider the Ethereum blocks based on the Poseidon 2 hash on a 254-bit prime, as well as the EDDSA signature, we could get real-time proving from a browser on an Apple M4 Max. But the question here, we are not talking about modifying the Ethereum stack. So really, we're asking, can we do this on a browser today? So if we compile RETs to WASM, which is what most people are doing in the zkVM space to prove Ethereum blocks, today on a browser with the Ligatron system, our projection is this is going to take 25 minutes. I think impressive as it sounds already that we can prove a block on a browser. I mean, this is not real-time proving. So the question I want to not question, but I want to tell you the direction we are taking, where we think the current state can be proved, let's say from a commodity laptop. Google Wallet recently incorporated a zero knowledge for identity verification. That's not very important. It's nice, but not very important. I want to talk more about the tech stack they used, where they had used Ligero as part of it. And they used a combination of primes. If we do the same, where we could do the catch-up side of it on the GF and the ECDSA on the prime friendly for ECDSA, our projections indicate we should be able to do it. So follow us on on X. You will find out by Q3. Thanks.
Thank you, Muthu. Any questions, feel free to unmute or raise your hand or ask it in the chat, and I will be relaying the questions.
Good.
Okay,
open source,
one question.
very quick question. Yeah, I saw the open source question. We're going to open source it. We said July, but we hope to do it like in the first 2 weeks of June.
Okay, amazing. I will be updating my tracker for June. Thank you again, Muthu. Next up, we have Miden.
Hey, everyone. Can you guys hear me?
Yes.
Awesome. Thank you, Justin. Hello, everyone. Just want to say a few words about Miden. Miden has been kind of open source VM for a while. I've been working on it for a few years now. I think, to summarize Miden, it's a custom ISA. It's not a ZK. It's not a RISC V VM. And we prioritize a few things like specifically safety, recursion friendliness, and client-side proving. And I'll talk about safety features in a second. But recursion friendliness, for example, where our goal and what we're doing with Miden is that we use the same VM both to execute programs and to recursively verify itself. So we don't have 2 different VMs, one for recursion, one for the baseline ISA. And then the client-side proving, we try to be memory conscious and with small proofs and things like that. Our proofs, then you'll see later, is like 80 kilobytes to 100 kilobytes in size. And overall, we can, for programs that we care about in the context of like proving relatively small programs, we can do it at actually, just with a few gigabytes of RAM. Miden is a Stark-based VM. We are migrating to Plonky 3 over the summer. Right now, we're using Winterfell Prover that I wrote a while back, but we will be moving to Plonky 3. I think there are several unique features to Miden, which, besides the custom ISA, make it really different. So, for example, it is not a von Neumann machine. Instead, we have the Merkleized object syntax tree-based program representation. It has a couple of interesting properties. For example, you don't have call by memory address. You do call by hash, which makes dynamic linking much more safer. Like you always know what you're going to be executing when you make a call to an external function. You can hide parts of the program and basically reveal only parts of the program publicly, and whoever needs to verify the program doesn't actually need to know what all the branches that are taken in the program. In the VM, we also have multiple isolated contexts. So you have memory isolation enforced by the VM itself. We also have this notion of configurable kernels, which we can basically use to enable this interesting approach to precompiles. I already mentioned the proof size is fairly small. Another important thing for client-side proving is that there is no startup time. You can basically start executing useful program within a first cycle of the VM. So sometimes you can have a program that executes just for 5,000 cycles, and it's very, very fast. The way we're working with the compiler is that we have a RAST compiling to WebAssembly components, and that gets transpiled to Miden assembly. WebAssembly components are here interesting because it allows us to kind of enforce this no shared semantics between different modules. So this memory isolation that I mentioned before wasn't components enforced by default. And yeah, there are a few things we're working right now on. Precompiles being one of the things we want to do with precompiles is that adding a new precompile would not affect the circuit of the VM, so you can use the same verifier regardless of the number of precompiles. And then our target is to have the EVM proven on Miden. Once we have precompiles, this is one of the major blockers, but we'll be able to do it hopefully in Q4 of this year.
Amazing. Looking forward to EVM proving. We're over time, but I'll just relay the last question real quick from Giacomo. When multilinear proof system?
We're looking into that as well. Maybe with some of the new Jagged PCS stuff, it could happen sooner rather than later.
Okay, fantastic. Thank you again, Bobin. Next up, we have an extremely unique VM and project called the Nock VM, and I'd like to invite Logan Allen to the stage.
Hey, everybody. Been a crazy last couple of days because we just launched our ZK proof of work system Wednesday. So running on a little bit low sleep right now, but we've got Nock zkVM. It's what we view as the minimal zkVM. We support 12 base instructions alongside arbitrary extensions, which we call jets, supporting custom math and cryptography. At the beginning, we've only written tip5 hash support and Schnorr signature support using cheated curve, which Toposware created. We have formal results showing 121-bit security level using the Goldilocks prime field, alongside showing that we have a 10x more efficient wrap than existing RISC-V systems in terms of trace and gate counts. So particularly, our trace is we have linear rows to opcodes in memory, and our trace is tiny with 395 field elements with only 175 degree for transition constraints. And that's notably for a Turing complete zkVM here. So we have a preprint with formal results being released in 2 weeks. And the Nock zkVM, notably an earlier version of it, is already open source and incorporated into the ZK proof of work chain we just released 2 days ago as its proof of work puzzle to start bootstrapping proving capacity broadly and basically instantiate a performance competition around hardware. So notably, we've spent almost all of our time in ZK research strictly on the wrap, so that we can basically move it between different PCS schemes. And so obviously there's a lot we can do to move it out of what it's currently in, which is using Goldilocks and starts. A lot of investigations to do from here, but we're really excited to have gotten the actual proof of work competition out to the public and going to have this preprint out with these formal results very shortly.
Amazing, just on time, Logan. So you have this extremely minimal zkVM, and I guess one of the things that makes you unique is the proof of work aspect. Is the idea to try and bring in tens of millions, maybe hundreds of millions of dollars of incentives to go build Snark ASICs?
Yeah, that's exactly right. So the concept here was we saw this large mismatch between the existing VCs providing lots of money to prover hardware acceleration companies without necessarily already having sustainable business models for those types of companies. And so we saw a demand mismatch where there's until proving gets to have a good enough dev experience and is easy to integrate into existing applications, it'll be rather difficult for those types of companies focusing on ZK hardware acceleration to actually have sustainable businesses. And so what we wanted to do is to try to fix that incentive by providing a block subsidy for ZK performance research made practical in the real world, so that we could try to commodify ZK proving.
Okay, perfect. Thanks again, Logan. Next up, we have SP1 Hypercube, which seems to be a totally from scratch rewrite, an independent project from SP1. And I'd like to invite Ron Rothblum to the stage.
Everyone, let me just share this. Can you see it and hear me?
Yes.
Okay, great. Hi, everyone. I'm Ron Rothblum. I'm head of cryptography at Succinct, and it's really a pleasure to introduce SP1 Hypercube, our new version of SP1, which we're really excited about. And we released this week as part of the real-time proving announcement, which John will elaborate on later. So let me focus on the proof system. So SP1 Hypercube is a multilinear-based proof system. We've found multilinear polynomials just much more flexible and fun, to be honest, to work with. A lot of things that are difficult with univariates turn out to be much nicer with multivariates. As part of one of our main technical contributions is this idea of a jagged PCS. So we released a research paper about it. In a nutshell, the idea or the observation is that in the context of a zkVM, we want to commit to the computation trace, which has this sort of a jagged structure. So we have a bunch of tables that contain columns of different heights. We want to commit to them. In a traditional Stark-based proof system, you commit separately to each column, and that comes with significant overhead. The idea in jagged is to pack all of these columns together and commit to them as one multilinear, but still be able to emulate the kind of jagged structure. Using jagged, we were able to solve two of the key problems that we had encountered previously in zkVM design. One is the fact that, at least in a Stark-based proof system, the column count really introduces a major overhead. So as you want to introduce more columns, you pay quite a lot for them. Jagged gets rid of that. A second problem, which is a really key one, is what's known as a combinatorial explosion or the shape problem, which is the fact that, again, in a traditional system, you have a lot of branching based on the actual column heights. And this branching, which might be different in different shards of your proof system, causes a kind of major difficulty, I would say, in recursion. And jagged also solves that. It's also quite a lightweight protocol, so I hope others will use it as well. In terms of performance with SP1 Hypercube, as compared to the previous state of the art, which was SP1 Turbo, we're seeing a 5x improvement over tasks like Fibonacci and Loop, in which the underlying proof system can really shine, and very nice 2x improvement for precompile heavy workloads. And this was kind of a big part of the real-time proving achievement, I would say, and I think John will elaborate on that later.
Okay, perfect. Also just on time. Any questions for Ron? I guess one from me is that I think in your research, Ron, you've been pretty forward-looking, I guess, naturally as a researcher. Like, how much juice do you see is left in improving the proof systems? You've introduced a kind of 2 to 5x optimization with this new proof system. Is there much more juice to squeeze?
I feel that there is. There's plenty on different axes. Mutu mentioned memory, which I've personally been really interested in, worked on for a long time. So collaborated at some point. I think there's plenty there. In terms of time, I think there's quite a lot more to be done, both on the research and engineering.
Got it. Ron, thank you so much for the presentation. So we will be going back to my slides real quick. Okay, so the other thing that I wanted to highlight is the sheer number of integrations that we're expecting in Q2. That is, by the end of next month, we have 10 integrations that we're expecting from zkVMs. And so what is today a fairly bare bones website with Ethproofs with only 4 integrations should dramatically grow. So if you would like to integrate with Ethproofs, make sure to contact Will Corcoran, who will be helping with coordination. And in addition to the zkVM teams integrating with Ethproofs, we have 2 new pure prover integrations that are expected, one from Cysic and one from Fermah, both of which you'll be hearing from later today in the presentation. Actually, you'll also be hearing from Snarkify and ZkCloud. So these are entities that haven't designed their own zkVM. They're reusing existing zkVMs, and then they're providing prover services for those zkVMs. So a total of 12 integrations, hopefully by the end of June. Okay, well, that's the end of my slides. What I'll do now is open it up to the EFers to give various updates, starting with Alex Hicks on the real-time proving grants.
Yes, thank you, Justin. I'll just share my screen quickly. Oh, there we go. Okay, you should see it now.
Yep.
Yeah, so fairly straightforward. I think, as was mentioned last time, essentially, we want to make sure that we're supporting the teams which are pushing performance and getting us towards real-time proving. Obviously, with SP1 Hypercube and Risero's recent announcements, it's clear that we're essentially very close to getting there. And so just wanted to formally announce, and I guess following up on the last call, we are going to offer 3 $100,000 prizes. The eligibility for these prizes is to prove 99% of blocks in under 12 seconds. The payouts are structured in 2 payouts. So you get 50K after the first month, 50K after another 5 months. And the criteria is also to have an open source prover. It's first come, first serve. I suppose that for Succinct and Ligero, it's just a matter of time until that's done. And obviously, we're very much on the lookout for a third person or maybe a mysterious competitor that will come up and steal a prize.
Okay. Jordi asks, any minimum security level? Good question.
I think right now everyone seems to be on the same page with respect to 100 bits. I think that seems like a good baseline to work on. And Ethproofs has 128 bits, listed as a green piece of slice. But I think for now, 100 bits is a good baseline.
Okay, any other questions, just feel free to unmute. Any requirements for the amount of GPUs, i.e. hundreds of 4090s may not be feasible?
I think obviously the prizes are kind of indicative of maybe where we'd like to see costs go, right? If someone wants to spend $1 million on GPUs to get, 100K, I think that's up to them. It should be fine, I think.
Yeah, and we'll see in the upcoming presentations that the number of GPUs may actually be very, very reasonable to get to real-time proving. Thank you, Alex. Next up, we have Ignacio, who will be talking about proofer killers.
Yeah, let me share the screen for a second. Can you see my screen?
Yes.
Yeah, so I just wanted to do a quick mentioning on this zkVM benchmark suite that we have been working in the last weeks. This is joint work with Kev, Powell, and Mario, also from the EF. And I also want to mention previous work from Connor from Proof Labs and Ivo from Consensus that have also done previous work on zkVM benchmarks. So the idea here is to have some kind of standardized benchmarks for opcodes and precompiles that is not only covering average cases for proving blocks, but also worst case scenarios or challenges for zkVMs. So the idea is to have a corpus of this kind of benchmarks so we can run in multiple zkVMs and multiple EL clients compiled to the zkVM targets. And also as core developers, we want to quickly iterate on which protocol changes we have to do to really align more to zkVM proving. So the general strategy for this is leveraging the existing execution spec test repo that all EL clients already support for running tests. So we can create all these benchmarks that you can run on multiple combinations of zkVMs and EL clients. So the idea is that if you are a new zkVM, you can integrate to this zkVM bench repo, and you can run all these standardized tests, and you can see how your zkVM behaves on these challenging scenarios or how it compares to others. So here are some links to this to the zkVM latest release, which already has some really good coverage on precompiles and opcodes, and kind of also attacks related to some protocol workings, and also 2 links to relevant repos that I think Kev will be talking later. So yeah, that's it.
Okay, thank you, Ignacio. Any questions for Ignacio? I think the goal here is, to try and standardize as much as possible the benchmarking of the prover killers. As we'll see very, very soon, we have this new page on Ethproofs dedicated to killers, but it's completely empty. And part of the reason is that it's been surprisingly hard to benchmark these things. We've had all sorts of crashes and file format issues and also a bit of a barrier to entry to crafting these killers. But go ahead.
I have a question on the prover killers. Do we need to generate a proof that's verifiable on chain?
No, because we are mainly interested in proofs that will be verified by attestors. So at least that's kind of the main idea.
Okay, understood. Thank you, Ignacio. Next up, we have a very interesting development called the killer's killer. So there's a new research idea from Julian and Kev that possibly is going to remove the worries and issues that we have around killers. So Julian, the floor is yours.
Yeah, thanks for having me. So I'm here to give an update on this new research by Kev and myself. And Justin came up with the name Killers as it solves problems related to prover killers. So as we know, prover killers cause issues because the builder of slot n makes a block and gains the profits of it, but the prover of slot n+1 incurs the costs of actually making this proof. So the system is not incentive compatible. And so Kev and I proposed a mechanism that does achieve incentive compatibility, and what it does is it assigns responsibility of proving block n to the builder of block n, but enables the builder of block n to force include the proof into the block of slot n+1. And we do so by leveraging a for-choice gadget that's been best described by Francesco in view merge. And it's a for-choice gadget that's used as well as in Fossil and in MevBurn in all of these designs, basically. And what it does is a tester is locally observe a proof, and they observe whether that proof was on time or not. And they force the builder to include the proof if it was on time, and if the builder couldn't have seen it on time, then it doesn't have to include it. And so what we allow here is we gain the benefits of delayed execution in that there's more proving time, but we keep the benefits of the incentive compatibility of having the proof attached to one specific block. So a key part of this proposal is that we need to set a proof observation deadline, and that means that real-time proving might have to be slightly faster. So for example, it could be within 10 seconds, but it does gain us that we get this incentive compatibility, and so prover killer blocks aren't as problematic because the costs of proving are then associated with the person that gains the benefits from the block. So we gain incentive compatibility. So if this was hard to follow without a laid out timeline, or if you're interested in more details, I'll post a link to the ETH Research post in the chat, and you can text me as well. But just to reiterate, we solve incentive compatibility of prover killers by assigning responsibility of proving block N to the builder's block N.
Thank you so much, Julian. The link to the ETH Research post is in the chat. And yeah, basically the idea is that if you're the proposer at slot N and you propose a prover killer, well, you're DOSing yourself, you're griefing yourself, because now you're also responsible for generating the proof. And if you can't generate the proof, you miss the slot and you get penalized. So yeah, it's a very, very nice idea. And the way that I think about it is that we don't need the zkVMs to prove every single block, including worst case blocks, in 12 seconds. We just need them to prove economically relevant blocks most of the time, and 99% seems sufficient to me, even though a little bit more economic analysis is required here. I'm not seeing any questions in the chat, so I'll move on to Kev, who will be talking about zkBoost and various other initiatives he's been working on.
Yeah, thank you. Let me share my screen. Okay, can you see my screen?
Yep.
Oh, cool. Yeah, so the goal here, yeah, as we all know, is to integrate the zkVMs into L1, possibly starting off with off-chain proofs. And yeah, if you're pretty astute, you'll see that my slides essentially look exactly like Ignacio's, and that's because he showed me it yesterday, and I just basically copied it. Now, the three initiatives that, sorry, let me move this out of the way. The three initiatives that I want to talk about today is guest program correctness, zkRESS, and zkBoost. The guest program correctness is basically us going to the existing EL clients and either helping or doing it ourselves, integrating a stateless function. So this is the function that actually gets compiled to RISC-V. I've put a QR code here for the ref one that we're currently working on, and we've reached out to Ethrex to see if we can also add them to the list. zkRESS, essentially once you have zkproofs, you can then have a more minimal client that essentially receives blocks, receives a proof, verifies the proof, and they don't need to have all the state transition, the logic for the state transition function in their code base. And this is what zkRESS is. We want to start testing end-to-end integration next week. If you DM me, I can give you a link for the public Telegram bridge that we have for L1 zkVM. It's bridged to our public Discord channel. And this is in collaboration with Ref, in particular Roman. I'll just move this out of the way. And the last one is zkBoost. Essentially, we could have the verification keys be embedded in the ZK stateless client, but a better abstraction layer is to have this other software that stores the verification keys, compiles the programs, and allows you to verify the proofs. And this is what we're calling zkBoost. Cool. Yeah. Thank you.
Fantastic. Yeah. So Kev is working on basically middleware to integrate everything, a little bit like MethBoost in the context of ZK. So it doesn't matter which execution layer client you're using, which zkVM you're using, there's kind of this common middleware to connect everything. Again, I'm not seeing any questions in the chat, so we can power on. Next up, I will be sharing my screen to talk a little bit about Ethproofs V2, which has been quietly launched yesterday. So there's all sorts of cool features on V2. We have these new charts. You can change the various timeframes. Hopefully, at some point, we'll have the 1-year time frame, and you'll be able to see the 10x exponential decrease over a period of 1 year. We have zkVM's page. So right now, we only have 2 zkVMs. It tells you the name of the zkVM and the team and all sorts of other information. We have a clusters page. These are the proving clusters. So here we have 4. It gives you information as to whether it's open source, whether the binary is available, or costs and latency, of course. We have this new page, the killers page, which is not yet populated, but should be very soon. And we generally have just more information on the website. So for example, here, if you open up, you can see a bit more information about the machine that's being used. So how much RAM is there, how many CPU cores are there, how much CPU RAM is there. And over time, we basically want to incrementally add more and more information. Oh, and another thing that is super cool that I wanted to highlight is the pizzas. So, sorry, there's too much going on my screen. So if you open up the pizza here, this is kind of heavily inspired by L2Beat. You will see 8 different pizza slices. And for each, you will have 3 different colors, green, yellow, or red. And yeah, there's also a dedicated page for the various zkVMs. So it tells you some information at the top, more information about the pizzas. And if you scroll here, it will tell you about the various clusters that are using this specific zkVM. So in this case here, SP1 is used by 3 out of the 4 proving clusters, and you can have some stats here for each, and you can drill down here as well. So overall, a massive upgrade to Ethproofs. Congratulations to the team who built it, and looking forward to integrate the dozen or so provers in the coming weeks. Okay, now onto the main event of this call. We're entering the real-time proving section, and I'd like to invite John Gillis from Succinct to talk about their recent announcement.
Hey everyone, yeah, thanks for inviting me, Justin, and everyone from the EF. Yeah, I think the Ethproofs initiative has been super productive, and it's really nice to be measuring everyone against each other, because I think it motivates us all to ship faster and ship real-time proving faster. Yeah, so props to them. Anyway, so I think on Tuesday this week, we announced like our latest numbers on real-time proving. I think this chart basically like summarizes our current state of numbers. Basically, from April 19th to May 3rd, we ran like a scientific experiment where we basically tried to prove using ref Ethereum blocks, every 10th Ethereum block. And the summary of that experiment was that we can prove 94% of the blocks under 12 seconds.
Wait. Watching.
Hey, sorry about that. Yeah, please make sure to mute yourself. Go ahead, John.
Yeah, so we can prove 94% of the Ethereum blocks in under 12 seconds. And we can prove, I think, almost 99% of the blocks under 13 seconds. So yeah, that's like the kind of current state of our performance. We think we can improve it a lot. Like right now, we ran it on 240-90 GPUs, but we think we can probably get the exact same numbers with like around 150. And I think we have a bunch of improvements in the pipeline that will improve performance across the board. So yeah, feeling really good about getting to 99% under 12 seconds really soon. And even maybe like a more ambitious goal would be like 99% of proofs in under like 6 seconds or something like that. And then, yeah, we actually have also this like visualization where we're proving these blocks like in a real-time fashion in a demo. Like this is like a block probably from like 20 seconds ago. And you can see that like our cluster is breaking down the proof generation into a bunch of steps, doing as much as it can parallel. And you can kind of get a better idea of the serial bottlenecks here by like looking at the span of the bars and stuff. And you can see that we're actually quite bottlenecked right now by the executor. But yeah, I'll stop here for my 2 minutes.
John, this page is absolutely amazing. I love it. And I heard that it was designed by you. Is that correct?
Yeah, I designed it, but another engineer implemented it. So shout out to him.
Nice. And I also heard that this was vibe coded.
Yeah, I think there was a lot of Claude 3.7 helping out with it. Yeah.
Nice. So one of the questions is, how many GPUs are you using and what type of GPU are you using?
Our cluster right now is set up with 240 90s, but for most blocks, we actually don't use all of them. I think for most blocks, we can scrape by with something closer to 100 GPUs. But basically, the mental model is like for a bigger block, there's just like more cycles to prove in parallel at like peak. So you just need more GPUs. I expect that if we 10x the L1 gas or 100x, you will need more GPUs as well.
How much power do you use on average in kilowatts?
I am not sure. I do think these 4090s have like some standard power draw rate, so you could probably calculate it out.
During the test period, what was the very worst block proving time?
I think the worst in that scientific experiment was something around like 50 seconds. And there was just some block where like it was using a lot of like BN precompiles, I think. And like our prover wasn't really like optimized for like spamming it at that rate. So I think that's something we can easily fix. It was like a parameter configuration issue. But yeah, there are some blocks that are really bad.
Okay, we have questions coming in. What is the peak VRAM utilization across all GPUs for a typical block?
The 4090s have 24 gigabytes of RAM. So we tuned our prover for that. But on the 5090s and other cards, they have like 36 to 48 gigabytes of RAM. And in those settings, the performance is like a bit better. But we just used 4090s.
Does multiplying the gas limit by 10x also mean 10xing the proving time?
Yeah, no, it doesn't, because basically like one of the things we did was we forked REST to introduce this functionality of sub-blocks, which is basically the idea that like you can split an execution of a block into separate chunks and then prove from there. So if we improve the gas, if we multiply the gas limit by 10x, basically, we just like split into more sub-blocks. And we just need more GPUs to like keep up with the rate of work that's being like queued up into the cluster. But yeah,
okay.
It doesn't mean 10x proving time.
One last question. Will having a single transaction with 36 million gas in the block slow down the proving? Will more broken down transactions help with proving?
Yeah, I think having a single transaction with 36 million gas with our current approach would definitely slow down proving, because there's kind of this like fixed notion of having some state and like applying the transaction on top of it. Now there could be ways to go around this by again like going to the ref layer even more. But I think there's like an EIP that's like trying to limit the max gas limit. And if that gets merged, that will help a lot with real-time proving.
Yeah, so that's EIP 7825, which I believe there's likely rough consensus on. Now the question is, which number should we use as the per transaction gas limit? Okay, thanks again, John, and congratulations on the massive breakthrough.
Yeah.
Next up, we have Jeremy from RISC.
Hello, let me just share my screen here. See, can you guys see that?
Yep.
Great. Yeah, so RISC has also been working on real-time proving. We have actually achieved real-time proving internally in cloud machines. However, we're less than I think like only 60% of the blocks or so we're at on the cloud proving. Largely that is due to the limits of the fastest executor we can get in a cloud. We, however, are purchasing a cluster because effectively our analysis shows we need a super fast executor that's like overclocked, along with very nearby GPUs. But we are currently projecting about 120K for the cluster build out cost to be able to hit a significant 90+% of the blocks. And we'll know the exact number once we sort of have real measurements on that. But we're very bullish. Now, by the way, I would like to point out that 100% of what we're using to do all of this real-time proving is open source. Both the GPU acceleration code as well as the orchestration code is fully open source. Just some real quick numbers. Our executors over 120 megahertz. We think there's a lot of room to improve that, by the way, through other techniques. But we're happy with that number right now because it gives us where we need for real time. Our proving speed per 5090 is about greater than 2 megahertz, and our recursion time critically is less than 200 milliseconds. We also anticipate significant near-term performance improvements on these numbers. They won't probably be 2x's, more like 30%, 40% here and there. But then we are working on a new version of the zkVM that's fairly radically different. That's going to bring a huge performance in the proving speed, because real-time proving is largely limited by recursion and execution in some sense, because you can go as wide as you want on proving times. It probably won't bring down the latency very much, but it should bring costs down even further. So.
Amazing. Wow. Congratulations on reaching real-time proving internally on 60% of the blocks. I did not know that.
Yeah, and that's a very large, that's like 200 GPUs or something like that. So it's also quite extensive. But yeah, so we're excited about that. And we haven't done a huge test set yet. So one of our next goals is to do a much wider set of blocks, tens of thousands, so we can get real percentages. But yeah.
And how many GPUs would be in that 120K cost?
So currently we're looking at 24 GPUs if we go with the 5090s. We may end up changing. We're still looking at two different options. Also I'm not a hardware guy, the something 6000. What we found, part of the reason we're able to achieve this is we've been able to stack multiple proofs within a single GPU machine. So we're stacking between 3 to 6 simultaneous proofs, and we were able to get significantly more GPU utilization that way. Part of this was figuring out how to tweak some memory things and such. But that's the current number. We're also really trying to target under 10 kilowatts. I don't know whether we'll hit that or not. We've noticed that we're not hitting max wattage yet for these devices. So we probably won't be able to know those numbers until we actually get into the real values.
One question is, does V3 accelerate the execution or help with the recursion?
It not particularly. It's primarily accelerates the RV32IM execution, which is why it'll bring down costs. We do have some other potential things we may be doing on the execution side that may massively improve the execution, but it's unrelated to the V3 work. And then recursion, I don't think we'll have much there for a bit either.
Where can I find what will be changed in V3?
We have not released the V3 source code yet, but it's more or less a complete rewrite of the circuit. So almost everything at the circuit level. This is basically using the new M3 arithmetization that comes from Irreducible and applying that to both our Baby Bear circuit and to the, we will also have support for a Binius version of the circuit. Most of the numbers I'm talking about, though, are on the Baby Bear version. We actually think the Binius one might give us even greater performance win, but I think there's more uncertainty there in terms of the delta and also the time frame. So.
One question from me is around the diversity of the stack. I understand SP1 did a complete rewrite with Hypercube. Are you reusing libraries like Plonky 3, or is it also a complete rewrite?
So what's interesting is the V3 is a complete rewrite of the circuit. We're using our exact same proof system. So that's actually going to be identical to the V2. That said, the nice thing about the V3 is architecturally, it's less tied to the way our proof system works. So we could move to something like a multilinear thing, or we could use existing Plonky 3 or something along those lines. And open source of V3, we will open source it when it is released. So we will not be using it for any, like once it is done, it will be open sourced immediately. We're just not open sourcing it during development. So yeah, all of this will also be fully open sourced. All of our goal is to continue to have anything that is production ready be open sourced. We're very strong believers in that as a company.
Amazing. And then final question for me, and this is meant to be a segue for the next speaker. How much time is spent on execution at 120 megahertz?
Almost like what's interesting is that execution runs until almost the end. And then, basically there's only a few seconds in which we do like probably 3 seconds or less for finishing up all the proving and doing all the recursions. So if you're looking at a 12-second block, it's probably, 9 seconds of execution or something along that realm. So yes, I think execution could be improved dramatically, but our current design, we're not expecting that to change in the current design that much.
Got it. Thank you so much, Jeremy, and congratulations on achieving real-time proving internally and also being fully open source, which is amazing. Our next speaker is Jordi from ZisK, and they have been working on many interesting things because they're a zkVM which is designed from day one for low latency, and so I'll let Jordi take it from here. Jordi, you're muted. Still muted.
Okay. Hello?
Yes, perfect.
You can see, let me see. Can you see my screen?
Yes.
Okay, perfect. Well, okay, so the main improvement, as you mentioned, that we released it the last weeks or the last 2 weeks, is the 750 megahertz. Let's say RISC-V emulator. Actually, it's not an emulator. It's just a transpilation from RISC-V code to Intel code. So that's why we can achieve this number. This number is very close. It's like only 4 times less than the real execution. So that's, I think that's an important measurement because this allows, the base execution, the single thread execution to speed up at the limit. Okay, so this is already implemented. As I mentioned, we are developing open source. We are an open source project, and we develop open source. So everything is open source, and this is our philosophy on that. The other thing that we are working right now, that is, we're adjusting a lot of the, we are in this process of adjusting the, this part that's highly parallelizable, adjusting the sizes and the times of the different pieces so that there is good balance between all of them. We are changing a little bit the schedule for this balance so that all the GPUs can work all the time, working in something. So this is something that we are working. Hope that in the coming weeks, we have all these ready. And also, well, we already mentioned that, but this 0.15 seconds, I think there is here still a little bit of margin. Maybe 0.1 seconds here for the full aggregation. So this is, with this, we hope to reach the real-time proving very soon, which is the goal from the first day. I don't like to give numbers because my philosophy is just we give numbers when we have something that's open source that everybody can verify and to show. But yeah, the target that we are is 12 seconds on that. Of course, future work, audit, formal verification, sub-second proving. We can talk about parallelizing instead of having a single processor, having like multi-processors and things like that. That can help a lot. But yeah, we can. This is the work that we are doing right now.
Amazing. Thank you, Jordi. And I just want to relay a comment from John Gibbous saying that 750 megahertz is mind-blowing for anyone not aware. It's definitely, compared to all of the competition, close to an order of magnitude greater. So congrats on that. That alone might have a massive positive impact on the whole industry. One of the questions we have is, on which machine did you achieve 750 megahertz?
No, just a normal, this is in CPU. So I mean, this computation, this we will call the minimal trace. This is not, it's the part that's not parallelizable. And this is just a CPU. I mean, and the important is not the number of cores. The important here is the frequency of the core. I mean, if we are being able to run in a, let's say, an overclocking machine, maybe going at 6 gigahertz, maybe instead of being 700 megahertz, maybe it's 1 gigahertz or 1.2 gigahertz. So it's the important. I mean, we are translating RISC-V to Intel assembly. Okay, so and translation is one RISC-V is, I don't know, 3, 4, 5 Intel instructions. Here in these instructions, we had also add the instructions to generate this minimal trace, which is what you need in order then for running again or doing whatever, but already in parallel, maybe machines on that. But this piece is, and this is just, I mean, it's just assembly and a transpilation trick. I mean, it's not relevant to the machine, and the relevance of the machine is what's the clock in the Intel.
Uma asks, what memory argument does ZisK use? Is 700 megahertz just emulation of RISC-V, or does it include the metadata for the memory argument?
No, for the memory, I mean, so you're referring to memory argument for the proving is very much, I mean, it's just a normal, I mean, we are just sorting all the reads and writes and then sorting out later on. Yeah, there is a special running thing for the memory, but that's just taking. But at the end, you run it again in different in different machines. For the execution part, it's that's a different thing. For the minimal trace, the idea is that we are just storing the reads, so that then we can execute a specific code in parallel. I mean, with different chunks in parallel, without needing the memory, because we already have all the reads. I mean, instead of accessing to the memory, we're just accessing to the transcript. So that's the main idea for this to run in parallel.
Nice. And Amar highlights that another exciting thing is that you support 64-bit. One question is...
This limits a lot. I mean, this reduces also the number of clocks, which is, it's also another, I mean, if you compare with the 32 bits, probably, I mean, it's not a 2x, but maybe it's, I don't know, 20%, 30% better, because we have less clocks in overall, in the overall system.
Right. And Francesc answered one of the previous questions. The machine is a 3.1 gigahertz server with 32 cores. One of the questions is, does Golang support mean that you support the G extension?
I mean, we are currently supporting just basic integers, multiplications, integers and multiplications. We are not supporting floating points, but I think that there is some emulation way to build that. And then there is other extensions that's more about bit modifications. I mean, it's bit instructions and things like that we are not supporting right now, but they should not be hard to support. We haven't implemented them, but all these, so going to a G, if we emulate, I mean, if we do this RISC-V, I mean, we substitute these instructions for emulated floating point, which in the context of blockchain makes not much sense. We should be able to support the RISC-V-G.
Got it. Jordi, thank you so much for presenting, and congratulations on this execution speed.
Okay, thank you.
Next up, we have Mo Dong from Brevis, who will talk about Pico.
Thank you, Justin. So we're today here to just give a quick update on where we are in terms of achieving real-time proving and also our Ethproofs integration. So Brevis Pico, we started the GPU acceleration implementation a bit late in the game. We started around March, but we were kind of trying to speed run this to achieve the best performance here. So we're very, very close to our first version of the GPU implementation release. And on one single card of 4090, we are achieving about 6 times faster performance than our previous generation CPU prover running on 192 cores. And Pico is a modular zkVM that we support both Colabare and M31 field on the GPU version as well, so you can still switch between different fields if you want. And we do have multi-server clustering supported, but right now that is not optimized and something that we are kind of working hard towards, and that's part of our effort towards real-time proving. And one thing that we also have a product that is allow a smart contract to access historical on-chain data and the run computation on top of that. What we call that as a ZK data coprocessor. We also have that ZK coprocessor GPU version available and integrated with the ZK VM we have as well. This is already powering some of the major DeFi protocols for reward distribution, such as like Euro Money, which is one of the rising star in the stable token ecosystem in Ethereum. So we are now quickly integrating with Ethproofs. We have all the API integration done yesterday, and we will go live very soon once we have our GPU 1.0 released. And for the pie charts, for the pizza charts, we have audit in progress and security review competition is starting soon. So if you are interested in participating in that, we wholeheartedly welcome you to do that. For the progress on real-time proving, we have like kind of a parallel implementation for optimized clustering. We expect this to be very ready in a few weeks. And we very much focus on reducing the cost and understanding prover killer better with public benchmarks. In addition, we're also working with a hardware vendor on specialized hardware design, co-design with the VM as well.
Thank you, Mo. You mentioned optimizing cost. How expensive do you think the cluster of GPUs will be to achieve real-time proving?
Yeah, right now, so we're estimating around 150 4090 to 200 4090, very much on par with like what other teams are presenting here. But we do think there's still a lot of room to improve on that. Both on looking at not only just like the VM part, but also kind of thinking about potential RISC implementation changes, and also like kind of eventually some feedbacks that we analyze from kind of looking at the benchmarks in terms of like how we think some of the layer 1 evolution can also be guided through this if ZK proving layer 1 blocks is something that we are interested in long term.
One of the questions in the chat is the work that ZisK did with the executor adaptable to Succinct and R0? I was curious if you think it might be adaptable to Pico as well.
So yeah, this is an interesting question. So we haven't really kind of looked into that yet. But Alan, not sure if you have any quick thought on that.
Yes, we do observe that executor plays an important role in the efficiency of the whole Ethereum proving, or in general the zkVM performances. So if there's any way that we can integrate a very fast executor, that would be great. So currently we don't have a quick answer to that on top of my head, but we could look into that.
Perfect. So Jeremy answers, yes, in theory, the approach should be usable in our proof system as well. Amazing. Okay, looks like we're out of questions. Thank you so much, Mo. Next up, we have Stefan from zkM, who will be talking about ZK MIPS.
Yeah, hi. Okay, so yeah, so for zkMIPS, since last meeting we released zkMIPS 1.0 in the early May, and it's already launched on the Ethproofs, and we can see that we have a really good performance there, and we currently, from our benchmark, our execution speed is greater than 20 milli per second on a single AMD EPYC CPU, and the proving speed is bigger than 1.3 milli hertz on a single AMD RTX 4090 GPU card, and so yeah. And then we also the code is and our code has been open source since we I think since the day one. So we are under the auditing right now, and the audit would be expected to finish in the 4 to 6 weeks, and then we some other works is the cluster proving, which is our zkProof network, and we finished the pipeline proving last week, and so that means we cut the we split the trace in different segments, and once we split the when generates a new segment, we prove it immediately. Yeah, it's quite different from our previous implementation, because before this optimization, we need to split all the we needed to generate all segments, then begin to prove. And we also optimize our stack to Snark web, because it's not for the Ethproofs right now, but it's for some other applications like the for the VM bridge on the Golden network. So on a single RTX 1940, it takes about 2 seconds for the wrapper to being 245, and about 2 seconds to generate the Groove 16 proof. Yeah, so basically that's the update for this month. Yeah.
Amazing. One of the questions from the chat is, what is the unit for 1.3 million? Is it MIPS cycles per
Yes.
second?
Yes,
Oh.
MIPS cycles. Yeah.
Nice, makes sense. And in terms of estimating the cluster size to achieve real-time proving, is it similar to what others have presented?
Yes, it's on track, I think. Yeah.
Nice. Any other questions? Okay. If not, let's thank Stefan again, and have our last speaker in the real-time proving section, which is acting as a segue to our next section on GPU proving. Ouyang from Snarkify, the floor is yours.
Hello, everyone. I'm glad to introduce you to Snarkify, a team focused on endgame ZK performance. Well, for people who are not familiar with us, over the past 2 years, we've built the world's fastest MSMs, won about half of the Z-Price competitions across GPU, MSM, WASM, GPU, FPGA, and WASM. And we've developed the fastest Halo 2 GPU prover that serves the Scroll mainnet. That being said, let me walk you through how we build towards real-time proving. Well, since real-time proving is already here, however, we still need ZK to be faster and cheaper with less compute. To achieve that, the most important metric we focus on is the GPU proving throughput, the number of RISC-V instructions a single GPU can prove every second, because this is the biggest cost factor. If you can prove 10 times faster with a single card, your cost will drop by 10 times, basically. The second key metric we look at is a RISC-V emulator throughput. People have discussed a lot at this meeting. Like this is a latency factor because after this emulation, the proving job can be scaled across many GPUs and be aggregated recursively. I'm glad to claim that Snarkify is ahead of the curve on both metrics. People have reported different numbers today. And we at Snarkify has already achieved faster than the 750 megahertz emulator speed. So people are asking, can other VMs apply the same kind of technique this team has done? We can confirm that because Snarkify has the same kind of technique and then we will achieve faster emulating speed at a slower CPU with lower frequency. On the proving speed side, we are on track to improve the single GPU proving throughput by several times compared to the reported numbers today. Our product will be live on Ethproofs Call around end of June, so please stay tuned. You'll see real numbers at that time. Okay, but last, Snarkify's superpower is simply that we can make any zkVM real time. So we build the full stack in-house from scratch, from primitives like fields, curves, and DTFRI, to RISC-V emulator, GPU prover, to the aggregation pipeline that gives us the full control of the proving stack. So we're looking forward to partnering with the most advanced zkVM teams. So if you are building a zkVM and want to enter the real-time proving territorial, Snarkify can get you there faster than anyone else. Yeah, that's it. Thank you.
Thank you, Ouyang. And yeah, one thing to highlight is that Snarkify is not building a zkVM, it's accelerating existing zkVMs.
Yeah.
And one very exciting piece of alpha that you just leaked is that you've achieved more than 750 megahertz RISC-V emulation. I'm curious, have you broken the gigahertz frontier?
Typically, we don't release performance numbers before we actually launch the product, but I think the answer is yes here.
Yeah. Okay, wow. I mean, maybe projecting ourselves into the future, we'll be living in a world where we can prove statements almost as fast as the underlying x86, which would be quite a development, especially if we imagine that, right now there's only a factor of 4 or maybe 3 delta between the emulation and raw speed, and this gap can be closed with ASICs potentially down the line. So quite an amazing development that, at least there's a plausible path to just being just as fast as x86 computation. Any questions for Ouyang? I mean, I have to ask it. You mentioned that you're faster on the shard proving as well. Can you give a little bit more color on how much faster you
are? Several times faster. We haven't have the end-to-end the shard prover end-to-end running yet, but we have moved all the trace generation to the GPU. So as much we try to make things happen on the GPU as much as possible. So actually, we can achieve several times faster than the reported speed today.
Wow, that's absolutely amazing. I mean, even a factor of 2 improvement just reduces the number of GPUs required roughly by a factor of 2. So that alone is a massive, massive development. So congratulations, and looking forward to the integration with Ethproofs at the end of June. And one thing that I forgot to highlight on the Ethproofs V2 is that we now have the multi-machine pages up. No one's actually submitting multi-machine proofs, but the idea is that if you have a cluster, you're welcome to submit proofs for every single Ethereum block. And I'm hopeful that we'll have, at the very least, SP1, RISC0, and Snarkify proving every block by the end of June. So congratulations again. This ends the real-time proving section. As promised, we're going to have a very quick break, and we have a little bit of a surprise that we'll share. So do feel free to stretch your legs, get a drink or something, and we'll be back in a couple of minutes.
Thanks, Justin. Yeah, as mentioned earlier, one of the people that has been doing some early studies on prover killers is Connor from Proof Lab. Unfortunately, I don't think he's on the call, but he pulled something together that we wanted to share with you. He loves hunting proof killers as much as anyone, so he made a theme, and I'm going to share this here in a second.
Beat that brand new zkVM.
Another one, man. They multiplying like spam commits.
Who's gonna stress it till it taps out? Ghost ride your zkVM straight into the bay. Through Peterson hash, now your stack can't stay. Trust me, bro, nah, I don't trust it. Your proof's like my scraper, hella busted. Phil got curves, but the gas too thick. Mainnet choke, make your verify sick. Copy paste repo, another lame sequel. Tweeting benchmarks, bro, they're deceitful. You recursive, dog, please pause. Nested so deep, made Santa Claus lost. Back end sweating, chain haul drama. Verify slower than your grandmama. Prover killer, slaying every fake VM. Say you're modular, stacks looking shaky, man. Tweet proofs, but you can't even verify. Proof lab laughs while another zkVM die. Every VC got a VM, they all the same. Control V code base, Control C fame. You change a little field, wow, real clever. Still can't verify, yeah, me neither. Threads on blast, mainnet slow. Back end melt like Bay Bridge snow. Docs say trustless, that's so fake. Trusted setup that your uncle baked. Prover trying to load sounds like dial up. Chain froze up, devs in denial, bruh. Curve so niche, can't even scale it. Stress test heavy till your witness bailing. Spin figure eights, run constraints and break them. Boot up, stall, yo, mainnet faking. Docs on docs, blogs on blogs. Proof lab laughing, your VM logs clogged. Prover killer, slaying every fake VM. Say you're modular, stacks looking shaky, man. Tweeted proofs, but you can't even verify. Proof lab blast while another zkVM. I drop entropy like E40 slang. Your prover crash, that's bang, bang, bang. Claim you're plunked, but you're just confused. Circuit sloppy, benchmarks bruised. Back end looking janky like scraper paint. Mainnet run, nah, it faint. Verifier gone, ghost in the shell. Another zkVM bid farewell. Prover crying, CPU frying, tweeting copium, whole team's lying. Docs still say, alpha release, proof lab swing, VM deceased. Hey, proof lab, zkVM graveyard shift. Too many posers, not enough hits. RIP to another stack. We out here killing dreams. Yada da me, Bay Area, hyphy.
Woo! Okay, we have a link in the chat to Connor's song. Congratulations, Connor. Everyone seems to like it in the chat. Plenty of very positive comments. And we're back from our break, so I hope you got to get a drink and yeah, stretch your legs. So now we're going to be focusing on prover technology that is going to bring us to the next level and help us get to real-time proving on a smaller and smaller power budget. So unfortunately, our very first speaker, Omer from Ingonyama, had a last-minute cancellation, but I do want to say a few words about Ingonyama. I believe they're like one of the top GPU acceleration firms. They have this library called Icicle, and they will help any zkVM out there, I believe, some sort of a consultancy model get faster. So if you're not aware of Ingonyama, do check them out as one of the potential options for accelerating your zkVMs. Next up, we have Supernational, one of the very first teams doing GPU acceleration for Snox, truly OG. And I'd like to invite Kelly Olsen on stage.
Awesome. Thank you, Justin. Yeah, so I'll just maybe give a quick introduction. At Supernational, we do high performance cryptography libraries as well as silicon. Probably most notably, we do the BLS signature library that's used by the Ethereum consensus layer. And just wanted to talk briefly about Spark, which is another 100% open source library that we have that's free for any team to use if they'd like. It's fully NVIDIA and AMD compatible, which is something we haven't really seen too much out there. It's used by some of the leading zkVMs. So as John mentioned, it is used by SP1. It's also, I believe, used by the RISC team. And it supports a lot of the core primitives in Core Snark and Stark acceleration. So we have kernels for MSM, NTT, LDE. We've done a lot of work on the various arithmetic-friendly hashes like Poseidon, Poseidon 2. And we also support a variety of fields with Spark, like Goldilocks and Baby Bear. And if anyone needs help with it, they're certainly free to contact us. We also do provide acceleration and optimization services. So if you'd like some primitives added to Spark, that's something we can certainly accommodate. We work on end-to-end proving acceleration. And obviously a big topic here has been around the RISC-V executor speed or the RISC-V emulation. We've done quite a bit of work on accelerating witness and trace generation there. And for those that are still pursuing client-side proving, we do a lot of work on x86, ARM, and WASM. So certainly feel free to reach out to us. You can ping me on Telegram or just get in touch by email. Thank you very much.
Thank you, Kelly. I mean, talking from experience, you give them any task and they'll just make it faster. That's what they do at Supernational. And yeah, thank you so much for making Spark open source. I guess one question I have for you is, how far do you think Spark is from optimal performance? Is there juice to squeeze? And same question for RISC-V execution. Do you think you can go well above the 1 gigahertz that was teased earlier today in the call?
Yeah, so in terms of Spark, I think there's certainly room for improvement there. One of the nice things is some of the kernels are actually already faster, are actually limited by the hardware themselves today. So as we see new, 50, 90 GPUs come out, Spark just, performs faster on those because many of these algorithms are memory bandwidth limited. And I think one of the other key things is that while Spark's a great library, a lot of the magic comes from orchestrating the kernels and sort of stitching them together. So the performance, I would take the performance you get sort of out of the box with Spark with a grain of salt because there is a lot of work to do when you actually integrate it. In terms of the witness trace generation, RISC-V emulation, yeah, I think there's a huge amount of opportunity there. Several times. I think most of it could get several times faster. I think that there are some alternative approaches that could be taken that some of the teams are not doing today in terms of putting inline assembly to sort of directly translate some of these RISC-V operations to like the matching assembly on x86. So yeah, there's lots of opportunity there.
Wow, you've heard it here first. Several times faster over the 1 gigahertz, so at least 2 gigahertz. The Ethereum Foundation would probably give you a grant to do that kind of acceleration. Or actually, many of the VC-funded teams on this call might also love to work with you. So very, very bullish on these potential developments. Any further questions? Just checking the chat. Yeah, we have John Gibbous and Jeremy, I believe both CTOs of RISC-0 and SP1 saying that you guys do excellent work. So congrats again. Next up, we have Zan with Guiming, who will be presenting. Guiming, the floor is yours.
Thanks, Justin. Hi, everyone. I'm Guiming from Zan and Intchains Labs. I will give a quick overview about what we've done at Zan and Intchains Labs on GPU proving. Our team would like to lower the barriers for using GPU in ZK to serve and to empower the ZK community. We have accelerated cryptographic operators such as MSN entity, sumcheck, etc. We have a GPU solution for kinds of proof systems such as Goose system, Hard2, Punk3, etc. Accelerating proof system requires optimizing GPU memory, memory bandwidth, and PCIe bandwidth. Maximizing the resource utilization is key to achieving end-to-end acceleration. The right table summarizes the performance improvements on the GPU. We achieved up to 121 times speed up over CPU. In addition to leveraging the ZK algorithm, we need to address circuit-specific computations. Our goal is to offload all computations to the GPU. Our next focus is on achieving real-time proving with as few GPUs as possible. Finally, I'd like to provide a brief introduction to Zen. As a Web3 brand of Ant Digital Technologies, Zen provides service for the Web3 community. Zen is powered by Intchains Open Labs. We also building Jovi and Ethereum layer to RWA. Thank you.
Thank you so much, and very, very impressive numbers. One question for me. When you say small number of GPUs for real-time proving, do you have a number in mind?
Maybe below 100, even 50.
Nice, potentially 50 GPUs. And would that be 4090s, or would you use the high-end 5090s?
Maybe 4090.
Okay, nice. I mean, the rough heuristic that I have in mind, which might be incorrect, is that the 5090s are about twice as much. So if you go to 50 4090s, that's only 25 5090s, which I guess would match the numbers that we got earlier today from Jeremy of RISC. I guess one question I have is, who do you work with in the space? We've heard from Supernational that their kernels are used at the very least by SP1 and RISC. Can you share some of the clients that you work with?
I think I don't think it's convenient to mention their name.
Okay, got it. But is it fair to say that you're a general purpose consultancy and basically you welcome any of the existing zkVMs, of which there's about 25, to come to you for GPU acceleration?
Yes, definitely.
Perfect. Let me check the chat. Not seeing any further questions. Okay. Well, it looks like we're slowly building a cottage industry of GPU accelerators. So that's the end of the GPU acceleration section. Next up, I need to check my schedule. We have ASIC proving, very, very exciting. We have 6 different teams that are going to be talking about their ASIC acceleration work, starting with Ming from Accseal. Mingyu, you might be muted. I can't hear you. Can anyone hear Mingyu? No. We still can't hear you. Okay, what about going to the next speaker, just to give you a little bit of time to fix any potential technical issues. Leo from Cysic.
Hi. Can you see my screen?
Yes.
Okay, yeah, sounds good. Yeah, so here I'm going to give an update on the hardware part about Cysic. Yeah, so as you know, Cysic is doing ZK hardware acceleration from the very beginning. And our design principle here is to say the ZK computation, from our perspective, or like based on our observation, is like dominated by this like two things. Like the first is element-wise operations on the arrays, and second is a data layout reordering operation, which will make the computation like for the next step like much easier. Yeah, so like we have this like Hypercube IR post is like on our like HiKMD. So like based on this like based on this observations, we can basically use this like ASICs or the processor arrays like to handle this like two kinds of operation, and then we use the embedded GPU to handle the edge cases, the corner case, which we might be like missing or like we might be like add in the future. Yeah, so for here, this like I'll talk a little bit more about the element-wise operation. So we have like native support for finite fields such as like Goldilocks, Baby Bear, like Mersenne, or like some others, and also native support for the hash function Keycheck, Blake, Poseidon to make this like course like much faster. And for some like simple cores, like we have dedicated cores to do this like simple arithmetic, such as modular arithmetic. And then like for the complicated ones, we like the Ps will share the cores, share the resources to do the job. Yeah, so that's for the first component. The second is a data layout reordering operation. Yeah, so like we designed this like symmetric topology for data transmission to make sure like the data transfer is like optimal on the hardware. And it's near the 100% of the network on chip utilization, and it's optimized for this like high demand reordering patterns. Like I'll speed up. Yeah, so here like I'm showing this like 4x4 P arrays. Like the P's like are connected by the DRAMs by the like layer 1, layer 2 nodes. So this is for demos. Like the actual like P arrays are way much larger, and we have the RTO development is like from the small arrays like towards the full array, which is like way much larger. And based on our estimates, we also have like reports on, I guess, also on HiKMD to see we can actually proving 1.3 million Keycheck functions per second on just a single chip. Yeah, so like we are looking for like, since we are close to our RTO freeze, we're looking for some like collaboration to see if you have some like new finite field or like new hash function, please let us know. So we can put it on the chip to avoid this like very big performance gap between like software and hardware execution. And yeah, so by the way, it's like Cysic network is also working on like real-time ZK proving for ETH blocks using the communities like cluster. So like for the previous testnet, we have like more than 4,000 GPU provers and more than 180,000 mobile verifiers. Like you can just run the verifier on the cell phone and also on the Raspberry Pi. Yeah, that's all. Thank you.
Thank you, Leo. Jill asked in the chat, is the RTL open source?
The RTL is not open source for now. Yeah, so like when we finish the chip tip out, like we will open source the RTO, like at least we will open source the P part, like for people to see if they can improve on that.
Riza asks, do you use HBM or what is the memory bandwidth? How much memory do you pack inside chips?
Yeah, we use like a variant of HBM. Like, yeah, as you know, like the actually like one big bottleneck in the ZK competition is like the memory. There are like several like kinds of like HBM. Like we are still doing some work, some exploring, and some research. I guess like we can probably like talk offline to see like what's the exact HBM bandwidth like we are using.
Do you prototype on FPGAs?
Yes. Yeah, we prototype on the FPGAs. But right now, as you know, like the FPGA, the frequency is too low, and the hardware resources on the FPGA is also like very, very short. So we are building like multiple PCBs where like each PCB have like multiple FPGA chips like to emulate the results, like to emulate our design, the RTO design of the ASIC. Like we will report the numbers probably like in the coming months on that.
Question for me would be, is your ASIC capable of accelerating generic workloads like the existing zkVMs? And if so, how much performance gain can we get, for example, on top of RISC 0 or SP1?
Yes. certainly you don't need this like 200 like GPU cards to achieve real-time proving if you use like Cysic hardware like in the near future. So like by our current estimation, like one single chip should be like I guess like 5 to 10 times faster than this like 1490 GPU cards. And we certainly will pack like multiple chips like in a machine. Like we have two machines. The first one is called the ZK Air, which is a portable machine the size of a MacBook charger. You can just carry around with you. And the second is a ZK Pro, which we pack like multiple chips in that one. Probably you just need a single ZK Pro machine to achieve like real-time proving. Yeah, so that's our goal. Yeah.
Okay, a single machine can achieve real-time proving. What would be the power usage of that single machine?
Yes, as you know, like we are doing the ASIC, so the estimation is like it will be around like 3 to 4 kilowatts. Yeah.
Okay, well, that's something I can run at home.
Yeah.
That's about, I guess, my oven. Thank you so much, Leo.
Yeah.
Actually, one last question. Anyone knows how many Kitchaks does a 4090 proof per second? I guess that's not a question specifically for you.
How I can stop. I guess like 1490 is around 10K, I guess. But that also depends on the like proof backend you are using. So the 1.3 million Kitchak, we are actually using a variant of zkBoost system.
Okay, Mingyu, are you ready to try again?
So can you hear me now? Is it better?
Yes,
Okay,
perfect.
cool. Nice. Okay, let me get the screen. Okay, so yeah, this is Accseal, which is a standard for ZK ASIC that based on China. So actually, last year we have announced our Gen 1 ASIC chip for ZK proof. So it was based on TSMC 12 nanometer process, and this does not use HBM. It is like normal LPDDR chip. So it's relatively like a chip processing. And here's the numbers. So basically, I don't want to emphasize it too much because these are a little bit outdated. But essentially, we have the chip like tape out successfully, and also we build the accelerator card. And finally, like we actually also build a few like machines that really like host those cards in an array. These days, we are actually aim for the Gen 2 ZK ASIC, and it's currently still under development, under design. Basically, we are aiming for to further improve the MSM and NTT unit that is already supported in our first generation ASIC. Basically, we are trying to optimize the mathematics of the MSM calculation, especially the elliptic curves, and also the architecture design of the NTT unit. And furthermore, like as we noticed, like there's more kernels that was introduced into the ZK protocols these days. So for example, we need to support more flexible like modular arithmetics and also various hash functions that needs to be put in. So currently our expectation is that it at least will be like 4 times faster within the same area cost compared to our Gen 1 chip. And at the same time, we're also trying to develop a little bit like more customized designs. So basically the first 2 generation ASIC are kind of general purpose that we integrate like various kernels in that. But we're also trying to design some customized designs for some zkVM protocols like Alio, like Scroll, like etc. Other things. So basically, it will introduce the instructions, like support the instructions of those protocols, and also we build like a micro pipelining that have customized and fine-tuned function unit for those specific functions, and also like specialized optimizations for various hash functions and the Merkle tree designs. Yeah, that's all.
Perfect. Thank you so much, Mingyu. I remember holding the very first ASIC at ZK Summit, maybe ZK Summit 11, and that was quite a breakthrough. And it's great to hear that you're already working on V2. Do you have any ETAs for V2, and which process would V2 use?
So for the design part, we probably want to aim for like at the end of the year. We probably want to freeze the RTL design and start the backend. And probably if everything goes well, we want to like tape out like next year. So for the processing, for the process of the, I probably It's a little bit difficult for us because, like in China, you know, it's not very easy to have access to the very advanced process. So we are considering like both the 12 nanometer, which is probably more available, or also like the 7 nanometer process.
Okay, perfect. I'm not seeing any questions in the chat. Mingyu, thank you so much for sharing the latest developments from Accseal. Next up, we have Michael from Fabric.
Hey everyone. Let me share my screen. All right. Well, thank you for the opportunity, Justin, and thank all of you for the amazing work you're doing in this space. We're really impressed that real-time proving has been achieved so early. It's pretty amazing, and we look forward to seeing what our hardware can do to advance that even further. Few things that you guys probably already know. The chip is coming soon from the fab. This is taped out a few months ago. And in the last month, I have not been on Telegram much. So for those of you not getting responses from me, it is because the chip is now most of the way to finishing. We had to sign off a package. We actually opened a Taiwan office. We have an ATE test socket and board that we just signed off. We rented that. We arranged test engineers on the production floor. We signed off what we call our EVB, and that's been sent to manufacturing. So basically, there's a litany of things that you have to do in advance of production, and we are doing those things. I hope to be back online in a couple months, pretty much. And within the next year, we are going to, I think, achieve real-time gigagas per second. I think it's going to come much faster than what people realize. And just one VPU server is going to be able to prove blocks in real time. So yeah, that's our roadmap. And Gen 2 has kicked off. If any of you want to talk to me about co-designing Gen 2 with the algorithms that you're coming up with, it's much better than I thought possible. So that's pretty exciting. And a big thank you to the folks who made our journey possible as well at Polygon and Risero.
Wow, quite an alpha leak here. So just to make sure I understood this, the claim is 1 gigagas per second proven on one single VPU server, which is 6 cards.
No.
No. Okay.
Just one VPU server can prove today's blocks in real time.
Got it.
Yeah, so
okay, makes sense. And what is the power usage of this one VPU server?
It's actually around the 3 kilowatt range.
Okay, nice.
Yep.
So basically, each card is roughly the equivalent of a GPU today.
Yeah, something like that.
Nice. So, did I understand correctly that you haven't actually received the test chips, but you're doing all of this advanced work with the test board in preparation of receiving the actual chip?
Yes. So we have a socketed board that basically the chip will go into the very first day that it comes out of packaging.
Mm-hmm.
We are actually, I think, about 2 weeks away from receiving the first wafers. But then after that, there's like days of packaging and then putting it on the test board, and then there's bring up. So the first day, your GDDR memory and all that stuff is not going to work, and you have to go through the process of getting it to work. So that's called bring up. So there's going to be a process afterwards, but we're really excited to receive real silicon.
Okay, well, I can't wait. And I watched one of your videos from a couple months ago where you basically explained a lot of the testing that you did with this like massive cluster of FPGAs, I believe, to simulate everything. And I could recommend this video, which was very, very interesting.
Yeah, absolutely.
No questions in the chat, so we can move on to the next speaker, Hugo from Intchains.
Okay. So thanks, Justin. So can you see my screen?
Yes.
Okay. Let me try to turn off my video. Okay. So let me introduce the CF Labs zkVM ASIC solution. We have the vision to accelerate real-time proving for Snarkify Ethereum. Actually, we are the joint venture for Intchains and Oracle Labs, and our partner Intchains is a Nasdaq-listed company, and it actually holds ETH as a corporate strategy. And in last 2 years, and it started to design the ZK ASIC solutions that we already accumulated many IPs such as NTT, MSM, SumChecker, and so on. We in the past 7 years, we already mass production more than 11 ASICs, and we delivered many miners, and totally we shipped more than 50 million chips. So we design miners for some projects, including Caspar, Aria, and so on. And so we have very mature supply chain. Our design target is like, actually we already designed Gen 1, that's for Aria project, and now we are going to Gen 2, that's for real-time proving. And firstly, it will for the 10 million gas diameter. But in the longer term, we want to design a Gen 3 that can support gigagas real-time proving. We think we could reach more than 20 times energy efficiency. And you can see the data from the right side. So based on the Ariel's project, we have more than 20 times improvements in the energy efficiency. And the power should be less than 5 kilowatt. And it will be a single box design, just like we did for the Ariel project. And we are working on an algorithm study, and we mostly are studying RISC SP1 and Ariel. Currently we don't have plan to build our own zkVM, and then we will build an LPG prototype and a silicon production. And usually it will only take 6 to 8 months for us to reach mass production. And the most important thing is that we want to build a kind of open solution, and we want to work with Ethproofs and the whole ZK ecosystem to co-design standards, as we have a lot of zkVMs. And we hope we have some joint R&D research and design with our partners, especially on the software and hardware co-design. That's all.
Thank you, Hugo. Yeah, and from my perspective, it's quite serendipitous that we have a company that's simultaneously an expert in ASICs, having delivered tens of millions of chips, and is also holding large amounts of ETH in the treasury. It's quite a unique situation. And I look forward to what you guys deliver. We're over time, and I'm not seeing any questions from the chat. So in the interest of time, we're going to move on to Radi from Irreducible.
Yeah, thanks, Justin. I'm gonna share you this slide, which is gonna go through our proving stack, and apologies if this causes minor headache to the people who are looking at the slide. And I'll say 2 things to start my speech with. Well, first of all, Irreducible took slightly different approach in a bunch of things on the stack. We took slightly different approach to hardware acceleration compared to companies like Succinct and RISC, who first mastered the VM design and are now adopting all of these 4090s and 5090s. And then on the other side, in comparison to our ASIC competitors, we did very heavily investigate hardware in the beginning, but we decided to implement a lot of cryptographic stuff internally as a sort of breaking down the performance of the proving stack across the layers. So I'll actually start top down. We are really working on WASM-based interface for our VM. We just last ETH call, Jim presented Petra VM, which is now an open source VM based on a custom ISA. So just for clarity, this is not RISC-V, and we have transpilation in between WASM and custom ISA being developed as we speak now. Petra is described in language called M3 that Jeremy mentioned. This is a new arithmetization framework for Binius, and Binius is a proof system which is also open source developed, but primarily developed by Irreducible, and Binius is slightly different than all the other proof systems that these real-time RISC-Vs are running on. So unlike other proof systems that are leveraging prime fields and frameworks like Plonky 2 and Plonky 3, Irreducible runs in binary tower fields, which are, in our opinion, way more hardware friendly and provide higher computing density. Binius was from the get-go designed for proving at scale, and we are actually very excited to see a bunch of companies now adopting cluster scale proving. So we are outside of the spec of a single server, and everybody's talking about clusters. Binius was designed for clusters from the get-go, and ultimately Binius operates on Atom cores. Atom cores are another custom ISA, this time really like in hardware, similar to ones that came out of, Fabric and other companies to mention them, but this ISA operates in binary tower fields, and today we have it running on FPGAs at 450 megahertz. One thing is that in Q3, we are planning to have end-to-end, basically acceleration WASM to silicon, and we will be releasing two things in parallel. One is our proprietary acceleration running on Supermicro servers with 8 FPGAs, but also, and this is probably a bit of alpha today, we will be releasing an AWS image so that all people who are interested in proving on top of Binius can actually take an image, run it in AWS, and enjoy the benefit of this custom computing. This is really community effort in terms of helping others adopt Binius. So, for the future projects who want to work on this. That's all. Thank you.
Thank you so much, Radi. And by the way, congratulations to the 121 participants who made it through 2 hours of content. I actually have a call starting very soon, so I'm hoping to wrap up. But yeah, I'm not seeing any questions in the chat, so I'll move on to the next speaker, which is Slobodan from Ponos.
Hello, everybody. Glad to be here. Today, I'll present actually Crypto CPU, our newly actually announced product. So briefly about the trends, we've all witnessing ZK-centric Ethereum roadmap. On the other side, we've seen a lot of progress in different kind of zero ZK proving algorithms. And what is very important to state is there is a kind of convergence in these kind of trends, mostly around RISC-V instruction set for witness generation, as well as around small fields plus utilization plus aggregation for memory, actually better memory utilization, and after that proof aggregation. Anyway, all this kind of algorithmic progress, as well as progress in programming optimization with respect to mostly GPU, have their limitations. And beyond that point, it's practically only custom hardware that may help, especially when it comes to latency, which is crucially important for real-time proving. So when it comes to crypto CPU, we are taking a little bit different approach. We are relying on highly flexible RISC-V architecture, and we are extending it in two directions. One is practically custom instruction set architecture for native support for RISC-V based trace generation, and on the other side for support for prime field arithmetic operations. On top of that, actually, we plan to, we already developed set of coprocessors that are supporting special function units for critical models and cryptographic primitives like entity, hashing, and so on. And by the way, given the trends I mentioned before, everything is completely hardware software co-designed so that it's practically adopted for segmented proof generation and aggregation in that sense. It's very important to state that the beauty actually of this solution is that the fact that RISC-V architecture is general purpose CPU, so that which practically means that we may optimize existing standard compilers and provide possibility for developer community that is widely adopting high-level programming languages like Rust to use it without any kind of problems. Yeah, it basically some benefits that it brings. It eliminates all kind of data bottlenecks that we've seen so far. By the way, we have been developing solutions in FPGAs, and we encounter a number of problems that actually motivated us toward making this kind of solution. All single modules and elements of a proof are accelerated on one side, but on the other side, we are providing flexibility when it comes to programming as well. The platform may function as a cloud-based service, but as well as a standalone device, which is a kind of DeepIn enabler, and as well as can be implemented on on-prem infrastructure solution. So it's versatile and with no migration cost. We hope to deliver more than 10 times speed up compared to state-of-the-art solutions, and not only speed up, but also to cut cost significantly. And for instance, if implemented in form of clusters, we expect huge improvements compared to state-of-the-art. And looking forward to collaborate with everyone in the community. Thanks.
Thank you so much, Slobo. And I am looking forward to all of these ASICs reaching production. And at that point, we will probably have a dedicated call just for Snark ASICs, but it's a bit too early right now. So that was the end of the ASIC section. We just have two final speakers before we wrap up. So I'd like to invite Vanishri from Fermah. And so that's going to be a quick section on distributed proving. And the idea here is that not only can we improve power by having better hardware, but we can also improve the power footprint by spreading the power across multiple clusters. It's possible Vanishri had to go to a call, in which case, let's close off with Norbert from ZkCloud.
I'll go after Norbert.
Hi everyone. Can you hear me well and see my screen?
Yes.
Okay, amazing. Thank you. So this is Norbert from ZkCloud. Thanks for sticking in the call, all of you who are still in. We are building the first universal proving infra for ZK, supporting any RISC-V zkVM. So this means we are flexible to swap as the performance of the different zkVMs evolves. We've been participating in Ethproofs since late March and are very committed to supporting the snarking journey of Ethereum. One of the things we've been doing since the 1st of April, proving every Ethereum block, it's running with single GPU, and we are basically posting all of the proofs to the Ethproofs staging interface. It means basically in the past 7 weeks, we've proven about 380K blocks with an average proving time of 1 minute and 8 seconds or something like that. Our current infrastructure is basically a cluster of 24 4090s, but we've got the capacity to scale to 200 GPUs, same 4090s as needed. And probably, as I hear, it's going to be needed to facilitate real-time proving in the first days, but then we'll see how things evolve. We are currently using a custom version of RSP, SP1 for proving, and multi-GPU proving coming soon. So that's something we are actively working on. We are exploring other zkVMs that are open source and also have the multi-GPU implementations open source. And regarding regarding real-time proving, as soon as open source zkVM and orchestration implementations are out there, we are going to switch and happy to start real-time proving as well, along with the others. Yeah, I think that's it from my side. Yeah, happy to take any questions, but I think we are a bit over time. Thank you.
Nice. I think my main question is, since RISC-Zero's kind of cluster multi-GPU code is open source, are you considering them as a next target?
Absolutely. I mean, we've been exploring RISC-Zero. They came out with R0 VM 2.0 sometime in April, I think. That's when it was open sourced, while SP1 came out with Turbo in January. So that's why we initially went with SP1, but actively exploring RISC-Zero open to others as well.
Perfect. And thank you so much for being an early Ethproofs integrator.
Thank you.
Next up, we have a closing talk, Vanishri from Fermah.
Thanks, Justin. We are a universal proof market. I have two updates. On zkVM integration, we have integrated with RISC-Zero and OpenVM and are locally generating proofs for RISC-Zero, and other zkVM integrations are in the pipeline. Looking forward to soon submitting proofs to Ethproofs. Our near-term goal is to integrate pretty much all zkVMs and submit proofs for some of the most performant ones. On another topic, I have an update on the research side of things. We are looking at the gap in the security definitions of proof systems. So the current situation is that the best formulation of soundness is for ZK snarks is simulation extractability. But this formulation, this definition assumes that the proof system satisfies zero knowledge property, and most zkVMs are not built with the zero knowledge property as a focus, and we don't have a proof. We don't have a definition against which you can prove security for proof systems in a proper manner, in the best possible manner. So we are proposing a new definition. So coming up with this definition is not trivial. Some people have already have been looking into this. Researchers have been looking into this, and we have a proposal, and we call it chosen proof extractability. And Alex from the Ethereum Foundation has kindly reviewed it. And if anyone else is interested, please DM me, and happy to share it, and we will publish this soon. Thanks.
Amazing. Thank you so much, Vanishri. And it's an interesting combination where I believe you have the strong academic background and you're working on the distributed provers. And so there's this interesting mix of snark security definitions and integrations with zkVMs. Love it. This was the closing talk. Thank you so much to the 100+ people who made it to the very end. And I'll see you all next time for call number 3. Thanks, guys. Bye.